Hello everyone and welcome. I'm Matsanine Bin Khatun. Today we're going to dive right in and start building our essential toolkit for statics. We're going to begin with the 4 fundamental quantities that honestly are the foundation for everything we're going to do in this course.
Okay, so let's set the stage. The entire field we're studying is called mechanics. And at its very heart, it's the science that helps us describe and predict how things behave when forces act on them, whether they're standing perfectly still or moving around. It's really the physics of our everyday world.
Now, mechanics is a huge field. As you can see here, it covers everything from solid objects to fluids. But for us, in this course, we're going to zero in on one specific area: statics. And that means we're studying systems that are in equilibrium, which is just a fancy way of saying they aren't moving. Our job is to figure out all the forces at play that let a structure, like this bridge, stay perfectly still and stable. So how in the world do we start analyzing something as big and complex as a bridge? You might be looking at that and thinking, wow, where do we even start? Well, the good news is, all of mechanics, it's built on just a few core concepts. You can think of them as the cornerstones of our field. That's right. I mean, everything we're going to do in this course, every single calculation, every design, it all boils down to understanding just 4 fundamental quantities. If you can master these, you are well on your way. And here they are, the big 4: length, time, mass, and force. You'll also notice the word space here. Really, that's just the 3D world our problems live in, and we use the quantity length to describe an object's size and position within that space. So let's get our hands dirty and break these down one by one.
Okay, so first things first, we need to set the stage for our analysis. Let's start with the 2 quantities that define the physical world our problems exist in: space and time.
First up is length. Now, the formal definition says it's used to locate a point in space and describe a system's size. But really, it just answers 2 simple questions. Where is it, and how big is it? It gives us the geometry, the scale of whatever it is we're looking at.
For example, just take a look at this beam. The lengths you see, the 2 meters, the 2 meters, the 1.5 meters, these are absolutely critical. They define the entire setup, telling us exactly where the supports are and where that force is being applied. Without these numbers, the problem is literally unsolvable. And our go-to unit for length, our standard, is the meter.
So, that leads to a really important question. Can we even begin to analyze a structure if we don't know its dimensions? And the answer, as you can probably guess, is a big no. Length is absolutely fundamental. It defines the problem itself. All right, our second quantity is time. It's defined as a succession of events. Now, you might be scratching your head a bit and thinking, hold on, we're studying statics, where things don't move. So why on earth does time matter? And that's a fantastic question. Here's the thing. Even though nothing is moving, we're analyzing that perfect state of balance at one specific moment. It's like we hit the pause button on the universe to look at all the forces acting on something at that single instant. So time provides the context for our analysis even when there's no motion. And of course, the standard unit for time is the second. Okay, so we've got our where and our when sorted out with length and time. Let's move on to the next 2 quantities. And these 2, well, they're really at the heart of what statics is all about. They describe the actual stuff we're analyzing and how it all interacts. Next up, we have mass. You can think of mass as just a measure of how much stuff is in an object. It's this property that gives an object inertia, its natural resistance to being pushed around. And here's why that matters so much for us engineers. An object's mass is what gives it weight, and weight is a force. In fact, it's one of the most common types of loads any structure has to deal with, from a simple bookshelf to a massive skyscraper. We measure mass in kilograms. And that brings us to our 4th, final, and honestly the absolute star of the show in statics: force. The simplest way to wrap your head around force is to think of it as a push or a pull that one body exerts on another. It's the language of interaction. So let's just pause for a second and think about this. Why is force the most important quantity in statics? Well, think back to the definition. Statics is the study of objects in equilibrium, objects that are perfectly still. What keeps them still? It's the perfect balance of all the pushes and pulls, all the forces acting on them. This diagram is a perfect example. Look at this block. We don't just care about one force. We've got a push, labeled P.
We have the block's own weight, W, pulling it down toward the Earth, and then the ground is pushing back up with what we call a normal force, N. And it's also resisting sliding with a friction force, F. Statics is all about figuring out how all these different pushes and pulls work together. And this, right here, is the absolute core of statics. For an object to be in equilibrium, to be perfectly still, the sum of all those forces, all the pushes and pulls, has to add up to 0. They have to cancel each other out perfectly. This super simple but incredibly powerful equation, this is pretty much the foundation of our entire course. Okay, let's do a quick recap. Here's a little cheat sheet for you, our 4 quantities and their SI units. We've got length in meters, time in seconds, mass in kilograms, and force in newtons. I'd recommend committing these to memory. A quick word of advice, getting your units right and keeping them consistent is absolutely non-negotiable in engineering calculations. So let's bring it all home and talk about why this all matters. These 4 quantities, they're not just abstract ideas from a textbook. They are the fundamental tools in every single engineer's toolkit.
Think of it like a step-by-step process. First, you use length to map out the geometry of your system. Then, you use time to pinpoint the exact moment you're analyzing. Next, you use mass to figure out an object's weight, which is a major force you'll always have to consider. And finally, you use the concept of force to analyze all the pushes and pulls that have to be in perfect balance for your design to be safe and stable.
And at the end of the day, this is what it's all about for us as engineers. As the source material puts it so well, the aim is to create a structure where the loads are appropriately counterbalanced, ensuring the bridge remains stable and safe. It doesn't matter if the load is from cars, or the wind, or even the bridge's own weight. Our job is to design a system that provides the exact right counterforces to keep everything in equilibrium.
So that leaves us with one final big question. We have our 4 tools, length, time, mass, and force. We know our goal is to make all the forces add up to 0. But how do we actually get started? How do we take a real complex thing, like a bridge or a part of a machine, and start applying these ideas? Well, that is the perfect lead-in to what we'll be covering next time. Thank you.